Okay, so we'll now have the last lecture of the day. That will be presented by Frank Ferrari, and Frank will be telling us about the SYK model.
Thank you very much for this opportunity to visit South Africa and this university. So I will indeed talk about SYK more precisely. Maybe I can call this lecture some introduction to the melodic limit of disordered models. So that's where SYK is. But also tensor models and matrix models. Okay? And so introduction to the limit of these guys and black holes. Because this is really the underlying motivation for these developments, or the main underlying motivation for these developments. So this is a huge subject, so I really don't know where I will go in 2 hours, but I will try to convey both part of the big picture at least and some details, so that you can, you have some overview of this stuff, and then you can look in more in the literature. So there are many words in the title. The one very important one is melodic limits. What are melons? What is the melodic limit? You have 3 types of models here, the disordered models. So as high-energy theorists, we're not so well accustomed to deal with disordered models. It's a very well-known standard thing in the condensed matter literature from the 70s, when people started to understand glasses, skin glasses, or ordinary glasses, etc. They started to use disordered models, and then it developed into many directions. So it's well known in condensed matter, not so much in our field. So I will try to explain what this is. Tensor models are more related to our field, but I think it's also very unfamiliar because the people who developed these ideas were essentially interested into the quantization of gravity by looking at discretization of higher dimensional geometries. And that's a program that has been followed by a few smart people, but this is a small community, let's say, and most of us didn't follow, so this is also maybe unfamiliar. And matrix models, so this is maybe more central to string theory or high energy theory. But the relation with these 2 other things is not completely obvious, and I will try to make it clear. So there is deep relation. So these are 3 classes of models, and then black holes in the middle. Because really, we do this to study black holes, and I should actually have it here. Quantum. We want to understand black holes at the quantum mechanical levels. We want to build and study models for quantum mechanical black holes. All right, so let me spend a few minutes on the big picture about black holes. So this will be very incomplete, but I want to at least make a list of important aspects of black hole physics that any quantum mechanical model that is claimed to describe a black hole should satisfy, should reproduce. Otherwise, it has nothing to do with it. So there's one property which is the quasi-normal behavior. This is the physics of the quasi-normal behavior is as follows. It's very elementary. When you do a small perturbation of a black hole, perturbation evolves according to some wave equation on the background of a black hole. And the fundamental properties of these wave equations is that the eigenvalues have some imaginary parts, which simply physically mean that any perturbation will eventually be absorbed by the horizon and fall off exponentially. Okay? So that's what happens for any black hole. Any black hole. And the mathematical statement is that any wave operator in the background where you have the horizon is never Hermitian. You always have eigenvalues with imaginary pieces, which just again translates the idea that the horizon is a one-way membrane, that information goes from the outside to the inside, and any perturbation from the outside eventually will decay because it will end up inside. Okay? So that's the quasi-normal behavior. In quantum mechanics, this is equivalent to the exponential decay of real-time two-point functions. So typically, you look at two-point functions at finite temperature, because you have some Hawking temperature generally. And this guy will decay exponentially at large time, and this lambda, this tau here, this time constant, is related to the quasi-normal mode in the black hole. So this is something absolutely basic. If you don't have these properties, you cannot have a horizon, you cannot have a. The second property, which is related to the first, is the property of the continuous spectrum. This means that the spectrum of your Hamiltonian in general should really be continuous. Why do you expect this in a black hole background? Again, just at the level of intuition, it's quite clear. It's related to the infinite redshift effect that you have when you have a horizon. If you have any energy gap in a system with a black hole, you can always bring this gap very near the black hole, very near the horizon. From the point of view of the observer at infinity, the gap can be made vanishingly small. Okay, so that's a basic intuition. So a system in a black hole cannot have a gap. And this is seen indeed, when you solve, again, wave equations in black hole backgrounds, they always have a continuous spectrum. It's very elementary. You can write down and study this and make green with the intuition I've just explained. So you need a continuous spectrum. And indeed, continuous spectrum and this exponential decay, as I'm going to explain, are related. Okay? So these are two basic things related to the physics of horizons at some very, very elementary level. Right. Now, so I will add items here, but I can just already comment on these two. Because that's inconsistent, so there's a big danger mark here. That's inconsistent with unitarity. These two properties. The reason is that all the quantum mechanical systems that will be considered and that are supposed to describe black holes, they're compact in some sense. So you very easily derive and understand in a completely generic way that their spectrum, is discrete. So the quantum mechanical models have a discrete spectrum. That's very clear. Think about maybe the most famous example. Think about the black hole in anti-de Sitter space. It's a black hole in ADS5. You know that this is supposed to be quantum mechanically described by n=4 super Young wheels on a sphere. So when the super Young wheel theory is defined on a spatial sphere S3. A quantum system like this, of course, has a discrete spectrum. because it's defined on the contact space. And that's completely changed. So quantum mechanical models have a discrete spectrum, that's first thing. And second thing, there's unitarity. You have unitarity bounds that tells you that two-point functions sort of are always greater than 0, even greater than some constant which is greater than 0. So there's no way you can have an exponential decay at large time. That's just impossible from unitarity. You can derive that again, it's not so complicated, using some spectral decomposition, etc. So, in a sense, you know, the contrast between these 2 points I made here and this basic results is a version of the information paradox for black hole. It's a very precise version of the information paradox for black hole. You cannot, you know, have these 2 things in a consistent way. There has to be some underlying phenomenon to explain this, otherwise quantum mechanics cannot work. And I'm going to tell you what it is, or at least the way we understand it in modern terms. But let me continue with strange items here. So let me put here item 3. You have a very large class of black holes which are very interesting, which are called extremos. So extremal black holes are the most elementary example is the Reichner-Nordström black hole. So a charged black hole when the charge and the mass essentially are equal in appropriate units. Okay? So that's sort of familiar. What is interesting with this extremal black holes, well, there are many things that are interesting, but so the important aspect is that first, the temperature is 0 for those guys. So there's no Hawking temperature for extremal black holes. Second, they have a non-zero horizon area. So they are macroscopic black holes, you know, with big horizons, big area. And third, the near-horizon geometry always has some anti-de Sitter tube piece. Okay, so these are 3 salient features of this extremal black holes. Again here, this is very strange. Here I can put another danger mark. Because this, if you believe in the Bekenstein-Hawking formula, if you believe that non-zero horizon area for a black hole means macroscopic entropy, it implies an enormous violation of the third law of thermodynamics, which tells you that at 0 temperature, the entropy should be 0. Of course, so this is a violation of the third law. Of course, we know a bit better. We know that the entropy at 0 temperature, which doesn't have any reason to be 0, the entropy is really the log of the number of ground states at 0 temperature. So if you have systems with degenerate ground states, you will have, indeed, a non-zero entropy. But what is really strange is to have a macroscopic 0 temperature entropy. It means that the quantum mechanical systems describing extremal black holes must have a huge degeneracy of their ground states, macroscopic degeneracy of their ground states. And that's extremely strange because the typical quantum mechanical models that you want to consider actually will have unique ground states. So it's you know, you can try to add symmetries and adjust things so that maybe you have a little degeneracy, but to have a huge macroscopic degeneracy as required by this extremal black hole, that sounds very strange. It's not the normal behavior for quantum mechanical systems. And this last item here, you have ADS2, so there should be some conformal, some emergent conformal symmetry when you look at things near the horizon, because of the redshift, that's some sort of low energy limit. And that's also a bit puzzling. It's not obvious how to devise models that will have this problem here. The last item I want to talk about, there could be others, but I will stop here, is chaos. So since my lectures are only 2 hours, I won't have time, unfortunately, to enter into any detail of chaos in black hole. But let me just give you, again, some very simple intuition about chaos in black hole. The chaotic behavior in black hole comes, in some sense, from the inverse of this redshift effect I was using before. It's the blue shift effect. So you can think about chaos in black holes as follows. If something very tiny happens near the horizon, because of the blue shift you might have, if something very tiny happens far away, when the tiny deviation, tiny effect you've had in, goes inside the black hole, it is infinitely blue shifted. And this infinite blue shift will be exponential. It's not difficult to derive that. So small perturbations outside can sort of, because of the infinite blue shift, become very important. So grow exponentially. And that's where chaos comes. Chaos is exactly this. Like a small effect can, under some conditions, become enormous and grow exponentially. So chaos is related to exponential growth of some observables, and the favored observables are these famous 4-point functions, out of time ordered, so OPOX, out of time ordered 4-point functions. So typically, you are looking at objects of this sort, A of t, b squared at temperature beta. And you expect this to have some exponential growth here, so lambda t, when t is not too large. Of course, when t is very large, eventually it will saturate. But when t is not too large, you start with this exponential growth. So this is what you expect. And there's something else. There's an additional nice thing here that is related to the idea that all this chaos is related to the infinite blue shift near the horizon. If this is true, the exponential growth, at least the leading exponential growth, should be universal. Because properties of black holes near the horizon are completely universal. They're essentially governed by their temperature or by their surface gravity. And you always get the same at leading order, whatever black hole you're looking at. So this picture of universality of black hole horizon implies that this lambda should be sort of universal. And lambda is supposed to be equal to 2 pi over beta, where beta is the inverse temperature. Okay? And so that's supposed to be universal. And this left-hand side is actually conjectured to be an upper bound on the possible exponential growth. So for any quantum systems under some conditions, it's conjectured that lambda should be less than 2 pi over beta, and this conjecture actually has been proven by Mandelstam and company in some special instance. So there's no full understanding of this for general, for example, the proof that is available do not apply to these guys exactly, but to similar guys, and probably it will be eventually proven to be general. I think people just didn't have time to sit down and make it general. But it's very likely that this is, so that this value is the fastest possible exponential growth for this correlation functions. Okay, so, sorry.
How is the calculation then?
So on the gravity side, yes, so you do the usual holographic setup for computing this sort of guy, and you find this is, like Schenker and Stanford, etc., and that's not very hard. On the quantum mechanical side, to prove that this is completely general, first of all, you have assumptions, large N sort of assumptions, etc., which I didn't explain at all here for the moment. And the proof, even under some assumptions, is for special guys that are not this one, or not even the most general thing that you want on. So it's not completely solid, but it's very likely to be general. Again, I think these are recent things. People are working on exciting, they try to make things advanced, and probably you need to sit down and wire to understand this, and hopefully it will be eventually done. So I believe it is true. So this is probably something completely.
And just to understand, can that C be more specified?
No, well, C really depends on details, but it will never be some exponential number. All right, so how are we going around this? And of course, the clue here, fundamental clue, is given by the holographic description of black holes, even though then you can sort of go further than the holographic description. That meaning you don't need to use a precise holographic setup, I think, to work on these models, but holographic gives you the general picture to expect. So the picture from holography is as follows. First of all, you always have typically a number, an integer, n in the models, which counts the number of degrees of freedom. In a very specific context, n, for example, is the number of brains you put into your strain background. Okay, so think as n as the number of brains, n d brains. So n is the number of degrees of freedom. And then there's this idea that classical gravity corresponds to the large n limit. More specifically, typically, the Newton's constant is 1 over n squared. This is what you would get in matrix model. Okay? So, this is a very deep, very important piece of information. A large n limit in some quantum mechanical description, so large number of degrees of freedom in some quantum mechanical description is related to what one would like to call classical gravity. That's very strange because, of course, n goes to infinity is something like a thermodynamic limit, large number of degrees of freedom, but it has nothing to do with classical limits from the quantum description. It's some kind of thermodynamic limit. It's not classical. But in the gravitational interpretation, it's supposed to be mapped onto classical gravity. And of course, you can go further. You would say, oh, then the 1 over n or 1 over n squared corrections here, so corrections to the leading thermodynamic limit, should be mapped onto what you naively call quantum gravity corrections.
Whether it becomes classical or not depends on how do you map your field theory observed to the so-called classical.
Yeah, that's right. But it's not really a classical limit. It's a naive or fake or I don't know, classical limit, or maybe these words are not appropriate. It's the classical limit that you had always thought of when you think about gravity. But it has nothing to do with the classical limit here from the point of view of the quantum mechanical description. The large n limit is not classical at all.
For case invariant operators. For case invariant operators, it gives you this large n factorization, which is an analog of.
Which is, yeah, but it's one feature, but it's It's not h bar goes to 0. And, all right. So, fine. Now, this also gives you some hints about how things might work when you think about the thermodynamic limit. The typical quantum mechanical systems, I said, are so compact sort of systems. So you would like to think about them as having some discrete spectrum in time. Maybe the simplest way to think about these systems is to start with the zero coupling limit. Start from some sort of harmonic oscillator. If you have a harmonic oscillator, then okay, all these spacings will be equal. And you have, of course, a lot of levels. And probably you remember that if you're at level n in a harmonic oscillator, then the degeneracy is very, very large, of course. It's exponential. So the number of states here is of order e to the n with some number here. So you have huge degeneracy at level n for a harmonic oscillator. Now, of course, our systems will not be harmonic oscillators, so they will be interacting. But if you turn on the interaction, the intuition about what is going to happen is clear. These degenerate levels have no reason to remain degenerate in general. So you have a lot of levels. You could do perturbation theory here and find out that you have a lot of levels, but it's very clear that you're going to have, this is as a function of some coupling constant in your quantum system, you're going to have a picture like this with a lot of levels appearing. Now, if n is very, very, very large, and I told that the degeneracy here is exponential, on the other hand, the gap between states is of order 1. This is just, you start here from harmonic oscillator, let's say, with order 1 jumps between levels. That means that the gap here between two successive levels is exponentially small. This is of order e to the minus n, e to the minus some constant times n. So gaps in these interacting systems are typically exponentially small. If you take the n goes to infinity limit, this really behaves as a continuous spectrum. And that's where you can make the link with the argument I already erased now and the properties related to horizon. So at finite n, indeed, your spectrum is discrete. But since the gaps can be so small, any large n approximation will wash out these gaps and you won't be able to see them. Seeing the gaps is non-perturbative in the 1/n expansion. So it's a non-perturbative quantum gravity effect if you think about the gravity picture. All right? So this is how large n reconciles quantum gravity with black holes and unitarity. At least that's how we think about it in the modern way.
How do the gaps go in London?
How?
Do the gaps go in London?
So this is a good question. No, so the gaps will always be e to minus n, so you won't see them. So it's a big continuous spectrum. Then what is happening?
In London.
I will tell maybe tomorrow some aspects of this. It's a big mess, it's not fully understood in general, but we understand it at least in some instances, which are interesting. All right. So because of this, you can have a continuous spectrum at large n, you can have exponential decay of two-point functions, etc., etc. So it can work, but it's a very messy and sort of complicated sort of systems that you typically have to use. And in particular, I should add that, of course, all these are completely non-perturbative in lambda. So you have to deal with these systems in a fully non-perturbative way in lambda, in the ordinary coupling constant for the quantum mechanics. So lambda is like h bar. So you have to deal with the full nonlinear quantum system on the quantum side of the description, but at large n. That's how you have to deal with
I'm
it.
sorry, lambda is like h bar, or is more like a curve?
Lambda is some sort of top curve. So now let's be a bit more precise. Start to make the link with some of the models I want to deal with. So what kind of quantum mechanics string theory suggests? That's the second big lesson from holography. So you have these brain constructions. Let's be very generic. Let's be very, very generic. So you have n d brains in a system, and the idea is that if n is very large, these d brains will become very heavy and somehow will be a black hole. But we know how, in principle, to describe quantum mechanical systems of d brains. These are objects on which you can have open strings that start and end. So the open strings have two ends, of course. That gives two indices to tell you on which d-brain the endpoints are attached. So one endpoint is attached to d-brain number I, the other endpoint is attached to d-brain number j. For any such string configuration, you have a mode, a string mode, so a field, if you like, with two indices. Let's call them x, I, j. And immediately you see that any string theory setup like this will yield variables that are matrices. So n times n matrices. Always. It's automatic. So what you always get from d-brain quantum mechanics is the matrix model, the matrix quantum mechanics. Another feature that I'm going to emphasize now, because it has an interesting twist in the story I want to talk about, is that these objects will typically have additional indices. And one index that they always have is associated with the fact that in brain constructions, you typically have, you always have, orthogonal directions to the brains. And so you have a symmetry group corresponding to the direction orthogonal to the whole volume of the brains. For example, if you have the free brains, then you have this SO6 rotation group, because the free brains live in 10 space-time dimensions, so you have some SO6 symmetry group around the stack of brains. So the x's have also this index mu. And mu is an index for typically some SOD, let's say symmetry group, corresponding to the rotations in the direction transverse to the brains. Let's write it because that's important. So these are the rotations in the directions transverse to the brain. All right. So these are very basic ingredients. And so what kind of Hamiltonian do you want to look at? Well, so you will just have the normal things. So you can have, of course, you have some kinetic. Okay, if I'm using the Hamiltonian, so you have some kinetic term. You can have some mass term, and then some interaction term. So interactions. If you quadratic, you can have interactions of this sort. You can have this one. You can have the famous combination of these two, which is the commutator square, and of course, etc. The higher order interactions. Of course, you don't need to have only one x. You can have x, y, z, etc. The x's can be bosonic, but they can also be fermionic. In typical string theory setups, you have both, because you get supersymmetric models. So you have both fermionic and bosonic matrices. Okay? So you can put all these ingredients together, but this is really the typical kind of Hamiltonian we want to deal with. Maybe the one you are most familiar with is if we come back to N=4 super-Young-Mills and ADS5 holography. In that case, these fields are just the Cahuzac-Klein reduction of the super-Young-Mills fields on the free sphere on which the theory is defined. In which case, indeed, you have an infinite actually number of x's. Okay? In that particular instance, we have to deal with an infinite number of x's if I want to formulate the problem as quantum mechanics like this, because I have all the spherical harmonics on S3. But this is not essential. You can also have models that involve not d3 brains, but d0 brains, which will be purely quantum mechanical. And then you have a finite number of variables. The general law is that to get black hole physics, you don't need these infinite things or this infinite number of variables or a lot of complications. The general law is that any generic model of this sort, matrix model of this sort, probably does have all the black hole behavior I was discussing before. Okay? So this is the sort of model you need to deal with in the large n limit. So large n for matrices means you have to sum up planar diagrams. Good. So do you have questions? So I think I will stop the general introduction and we'll go to more specific things. But the lesson is that this is the kind of models you want in principle to study. You want to do that at large n. This amounts to summing the planar diagrams. Of course, it's an extremely difficult thing to do. But in principle, you know the kind of thing you have to do. In principle, holography has given you, at least the setup that you need to study. Good. So now, let's forget for a little while, these matrix models, which really are the one I think that we should be looking at. But let's try to other kind of...
It's always matrix quantum mechanics, it's never really matrix.
It's a matrix, well, when I say model, it's quantum mechanics. Of course, as I said, it could be matrix quantum field theory.
Right.
And actually, all I'm going to talk about, applies equally well to, you could say 1 + 1 dimensional or 1 + 2 dimensional matrix quantum mechanics. So these x's can depend on time, but also on some space variable if you like. Then it's like d0 brain, d1 brain, or d2 brains, etc.
So you couldn't do that. Could it be just matrix model?
No, because then you don't have, all what I explained about black hole, the horizon physics is real-time physics. You need a spectrum, so you need at least quantum mechanics. And that's enough, I think, to capture. But zero-dimensional, you will never be able to discuss any real-time dynamics, which are the really hard and crucial questions related to unitarity and everything else. All right. Okay, so maybe some advertising. So these sort of models, 1 year ago, or 1 year and a half ago, 1 year ago, we had absolutely no idea whatsoever how to extract any reliable analytic result on them in the non-perturbative regime. So how do I compute, for example, some entropy or free energy, non-perturbative? Can I at least have some qualitative, I'm not saying exact at the planar level, even at the planar level, but even some analytic tool to give you some at least intuitive or semi-quantitative insight. How do I compute some two-point function? Can I have some analytical tool to derive this exponential decay of the two-point functions? Or even better, this exponential growth of the 4-point out of time ordered correlation functions, etc. All these questions were sort of here in the air. They had been in the air for maybe a decade. And we had absolutely no idea how to do that. Because the ordinary perturbative tool fails completely. You never see any of these properties in perturbation theory. And we had no idea how to resum planar diagrams for the interesting models. For any interesting models. For those who know, you could say, oh, matrix quantum mechanics, maybe we know a bit, right, from even the 70s. Indeed, when you have only one matrix, for example, you can solve the model. But that's far too simple. That's not describing a black hole. People believe in the old days that it might be able to describe a black hole. But the one matrix quantum mechanics, there's no black hole in it. So you need several matrices. So the models that are interesting immediately fall into the class that was completely out of reach.
But it describes the two-dimensional string.
It describes a string background, but not a black hole.
No, the string itself, and then how do you reconcile that with the fact that the string has a
You are an expert in this. You know that if they want to look at the non-singlet sector, if they want
does this. There is a black hole there. Just people decided to study it. It still remains to be seen which model of black hole is the simplest. You know.
So I think what I'm going to say is that if you look at the system with one matrix, you have two things. You have the system with one matrix in which you impose the singlet constraint. So you gauge the unitary symmetry and you look only at the singlet states. This is normally what you would like to do with a string theory. In this case, the model is completely solved. It's easy. Now it's mapped onto a system of free fermions. It's been known for a very long time. And you don't have any of the black hole properties I discussed before in that context. Now, you could say, let's forget about the singlet constraint, and let's still look maybe at non-singlet sector or no constraint at all, the full one matrix, one more mechanics. I think this guy probably is a black hole.
Right.
But nobody knows how to solve it either. So that's it. Anyway, so yeah, 1 year and a half ago, we had no idea. And I think the excitement over the last year is that we believe maybe we have some new tools in order to be able to say analytic things about these models that seems to capture the physics we want to capture. So it seems that this new way of doing approximations is interesting because it's qualitatively correct. At least that's what we do. Okay, so that's the evidence. Now, let's forget for a little while this, and let's talk about disordered systems. Disordered models. And I'm going to present what it is here, and we're going to discuss some very elementary level. So consider a model. So I'm not going to do SYK exactly because I think the model I want to do is slightly more interesting. And it's more, and it's not more difficult. Okay, but I will tell you what SYK is. It's very similar. Maybe this is it's a bit more interesting and maybe even more elementary or more familiar for students. So consider n fermions. Okay, so the psi's are fermionic operators. They satisfy the usual canonical quantization conditions for fermions. And you have n of them. So the indices I, j, etc., they go from 1 to n. So in particular, the dimension of the Hilbert space is 2 to the n. Okay? Each of these psi is like a qubit. So you have n qubits. The dimension of the Hilbert space is finite, it's 2 to the n. And maybe it's more convenient to normalize here, just for convenience of larger limits. So I'm normalizing my fermions with 1 over n. Just a convenient convention. And let me consider the following Hamilton. So I'm going to put the n in front again. I think it's sort of convenient to do that. And then I'm going to have the usual mass term. I, psi I. So if I stop here, this is just the usual fermionic harmonic oscillator. Okay, so you have each fermion level, each fermion state can be either occupied or not, and the energy associated with this is n. So just fermionic harmonic oscillator. And now I want to add interactions. So I can, for example, think about an interaction term like this, why not? Or others. Okay, I could have psi, 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 or I can have a lot of versions, or high orders, etc. Let's stick to this, which captures already a lot. This is a bit interesting because it conserves fermion number. I have as many psi daggers as psi here. So there's a U1 symmetry, in other words. So I could interpret that as some electric charge. So that's a model which is sort of nice in the sense that it has some electric charge, a little bit like the Heisenberg black hole. And now I want to add a coupling here. So one thing you could do of course, is to contract the indices here, like say I, J, J, or something like that. But then, this is well known to be far too simple. This would be then a standard vector model. So vector models, what are vector models? Well, they're just models with this kind of variables. Vector models are models where fields have one index, like this I. They transform here under some, let's say, representation of some group here, UN. And you make models that are invariant with these vectors. These are interesting models that we studied a lot in the 80s, in the 90s, because the large n limit is solvable, and they display very nice features. You have the cross level model, which is really spectacular when you want to learn what asymptotic freedom is, etc. You have the nonlinear sigma model that you can study, and many other aspects with this large n limit, which is interesting. However, this is all stuff, and it's too simple for black hole. These models do not display the continuous spectrums, they do not display any of the properties I want to discuss. So no black holes.
But again, you know, vector models reappear.
Yeah, they're going to reappear.
No, I said they appeared recently as models of high
speeds.
Now, high speed theory is not exactly, we cannot say anything about what happens there with respect to black hole and so on. So,
but I believe the fact that we know that vector models are too simple, that's my opinion.
You think a CF theory is simple?
I think the large n limit of these models will not display any black hole.
They are dual, so they will display whatever high speed theory will display.
But they don't have black holes.
High speed theory has black holes.
No, they don't even have radio nature.
Not in the phase which
it's gauge dependent. It's you don't have any. Okay, you don't have. Let me be precise.
Right.
You don't have any of the properties I talked about before in this.
Not yet.
You don't have quasi-normal modes. You don't have chaos. You don't have the continuous spectrum. You don't have the redshift. So I don't call that a black hole.
No.
If I want to be precise. And I think that's just related to the fact that these vector models are nice.
Because this high speed theory has been understood now only in one very special limit, which is the tensionless limit. If someone forced you to do string theory in the tensionless limit, you would be having very little stuff like that. So high speed theory might.
So maybe there's still some hidden treasure to dig out from the vector models.
Definitely.
But at least the standard one, we know they're too simple to practice. So you could say, these sort of things, so if I contract, okay, the simplest thing to do would be a model like this, right? I, J, J. This is too simple to Hamiltonian. It's nice, but it's too simple for black. So the opposite of this is to say, okay, why don't we try still with vector-like variables, okay? Because we want to be simple. Matrices are really hard. So maybe we can still stick with these vector-like variables. But the natural thing here is too simple. Let's try to compensate the fact that this is a simple vector. Let's try to do the most complicated Hamiltonian you can think of. And the most complicated Hamiltonian you can think of is just this. So maybe I want to use a notation that display the structure of so IKJL of UN. So let's do this, and let's assume that these couplings are anything random. So you pick up all these couplings in a random way. So you have like n to the fourth coupling, not exactly because you have some anti-symmetry and reality properties, but you have of order n to the fourth coupling in your system. Pick them randomly, and I can give you a probability law. Let's pick the simplest one, the Gaussian. Okay, so the lambda is Gaussian random variable. So you have a measure like this. I will have some coupling here, G squared. And this this lambda squared is simply just lambda ij KL lambda KL. Okay. Random Gaussian. So this is sort of great because you can, in particular, put this on a computer in a very elementary way. As I said, this is a system of qubits, finite dimensional input space. There's no mystery how you can compute on a computer this Hamiltonian. It's a huge matrix, but you can compute them and compute it and diagonalize it and play with it. And on the computer, of course, you can also pick up these couplings in a random way. So you pick one realization. It's a well-defined quantum mechanics. Okay? So the genuine quantum mechanical model you study, again, is one realization of the lambda. The statement here is that when n goes to infinity, so the leading order when n goes to infinity, of a single realization of the coupling will be equal to what you obtain by averaging over all the models with all the couplings lambda according to the Gaussian average. Okay? So this is some sort of law of large number, if you like. The intuition about this is not very difficult. The intuition is that a model like this has interactions with all the degrees of freedom. Okay? All the psi's interact with each other because the lambda couples everything. So you don't have a notion in particular of locality or of space at all, or of lattice with local interaction on the lattice. You don't have that because all the spins, all the psi's interact with each other. Because of this, when you're looking at self-averaging quantities, which are typically the extensive quantities, so the most important self-averaging quantity is the free energy. The free energy, you can think of it as being the sum over patches. But by summing over patches, since the coupling is random from one patch to another, when n is large, the system is very large, so summing over patches will amount actually to average over any coupling. Because at fixed coupling, the lambdas in one patch of size and in another patch of size is completely random, even at fixed or fixed lambda. And so then the result is the same as if you were to integrate or average over the lambdas from the beginning. So that's a very standard trick or result from the theory of spin glasses or of disordered systems in condensed matter. That's a basic thing that you have. So that's trick one.
Question. How sensitive is this trick to choosing some other distribution for your lambda?
Sorry,
Suppose you choose some other distribution for lambda.
Yeah. So under a very large set of distributions, this is supposed to be true. But this is, and the result is, again, this is a law from condensed matter. Because the question you're asking here has been asked for spin glasses, for example. And you can do numerical simulations to check that. The results do not depend on the detail of the distribution that you make. So you always pick the Gaussian because that's the one with which you can compute analytically. So the only reason why you choose the Gaussian is because you can compute analytically, and because numerical simulations and general intuition tells you that the details eventually will not happen. What is important is that it's a random thing. I don't know what I'm doing. Oh, this is
Blackboard for us.
This is very good. This is going to kill someone. Anybody has a question? Maybe. It's so bad. Oh, sorry. So that's part one of the trick. Part two of the trick, you need to know what self-averaging quantity is. I just said what it is. Part two. So the self-averaging observables, or quantities, they are typically like the free energy or two-point functions that we will be dealing with, like this psi I of T1, psi dagger I of T2. So objects that are extensive, you have to sum over all the spins. These are self-averaging. It's clear that if you don't sum here over I, you look, for example, just at the two-point function of the spin at the single side, that's never going to be self-averaging. Because from one realization to another of the coupling, the environment will change completely, the interaction of this guy with the others will change completely, and there's no way it will not depend on the realization of the coupling. Okay? So that won't self-average. But quantities like this, where you take into account all the spins together, will self-average. So you can do the procedure here. So these are the self-averaging observables. So typically that's what you have to do. So you compute f is the log of the partition function, and then, so that's the partition function for the given realization of your Hamiltonian, so the given choice of couplings. So again, this is, as usual, this is the sum over connected Feynman groups. And two-point functions will have similar descriptions. And then you average over the disorder, you average over the coupling. So this bar here means averaging over the lambdas. So you have your sum over connected Feynman graphs, and you average. What does that mean graphically? Just keep that in mind. So for the model I had, I had a 4 fermion interactions like this. And I have a coupling here that now. So when I want to compute this, okay, I can have very complicated Feynman graphs with many vertices that will be connected, of course, by propagators. I'm not trying to draw a particular graph, but in some graph, I have many